We're starting lecture 2 with, as usual, a review of lecture 1. So what we talked about, what we talked about in the first lecture was we went over dimensional power counting. So I'm gonna go over it again a little bit more systematically because I feel I rushed it last time. The starting point is the scaling transformation. Recall that in flat space, when we were discussing field theory, a classical field theory, we talked about passive and active diffeomorphisms. So they were coordinate changes, and we said the laws of physics should not depend on coordinates, right? Now, we talked about symmetries, right? That's when your Lagrange or your action was invariant under particular change of variables in the active picture. We talked about flat space-time. Lagrange just wrote down had relativistic symmetry, which meant that there were Minkowski transformations. So Poincare transformation, coordinate transformations, or symmetries of the system. The story of a normalization group starts with a different transformation, different coordinate transformation, change of transformation. It's called scaling. So you take x mu and define x mu prime, which is x mu divided by lambda. You can think of this as zooming in and out, right? Because all the points are, but in space-time, covariantly, right? So it's not just in space, it's also in time. I could do all sorts of things. I could rescale in space, depending on what symmetries I want to preserve. If I want to preserve only rotations, I can scale with some power of lambda in space and another power of lambda in time. If I scale space and time with the same power of lambda as I've done here, that's appropriate for relativistic theories. For non-relativistic theories, there are actually for any guesses for Galilean theory, what scaling is good? Think about it. There are, depending on your theory and what symmetries you want to preserve, you would define scaling differently. But in relativity, for relativistic theory, the way to do it is this scaling space and time with the same amounts. All right, so that means that the volume form is gonna change this way. I apologize in advance that I think QFT2, we're gonna change convention, and little d is space-time dimension. And this whole QFT2. So we have the action, right? An integral over, it's a local, it has to be local. That was a locality principle. Action. So this guy has a dimension of d, dimension minus d in mass. Therefore, Lagrangian will have dimension d, right? So now let's, for simplicity, consider this Lagrangian. So this is some arbitrary interacting scalar field theory I can write down, right? We said that based on dimension counting, the canonical dimension of phi scalar is d minus 2 over 2. This means that phi prime, because of the very fact that I can view these as passive transformation, it means that phi of x is equal to phi prime of x prime, and phi prime of x prime is this expression. So that S is independent of your choice of coordinates. Good? So this is the passive picture. Now let's think about the active picture. When we're not dealing with phi prime anymore, we're talking about phi of lambda minus 1x. When m is equal to, so to understand that, let's pick a particular case. When this term and this term are absent, you only have half del phi squared. That's your action, right? This is massless free boson, right? In this case, you can see that if you take this action without these two terms, S at m equals 0, Gn equals 0 is the same under this transformation, remains the same. It's the symmetry of this theory. So massless free boson is a scale invariant theory. This is scaling, it's invariant under it, so it's scale invariant. That is the basis of a lot of things that we're gonna discuss in quantum field theory. Is that good? Okay. And inclusion of these terms, if they are small, they would explicitly break scaling symmetry. Good. All right. Now, so far the discussion was classical, but you recall that when we were discussing symmetries, we said that in the quantum world, there's this Wigner's theorem that says that to every symmetry of the action, there corresponds a unitary representation of that group. Here, scaling is R, right? You're multiplying by just a real number, viewed as e to the power of some number. Now it's pretty clear there's R, right? Now, we're going to call that operator dilatation operator, d hat. This is to be compared to P mu, right? Translations and rotations and mu, right? These are charges. This is a charge. Okay, not to be confused with the superficial degree of divergence that we were discussing last time. All right, so here is as a field, as a field in the Hilbert space, this is the transformation we expect in this massless free boson theory. When you have masses or you have other couplings, this is no longer symmetry. So there's no Wigner theorem that tells you that there has to exist an operator in the Hilbert space that would do scaling for it, right? But if these parameters are small, there is a sense in which if the theory is not too crazy, you can still make sense of scaling. I want you guys to keep that in mind. This is the basis of perturbation theory in quantum field theory. Right? Okay, good. Are we good? Any questions? All right, so I went through scalar field theory. Let's give another example, the Yukawa theory. The Yukawa model is this. There is a scalar, the action of scalar phi is the same thing you looked at. Now there's a fermion, and there is this phi psi bar psi coupling, right? This is Yukawa theory model. So just based on dimension counting, the dimension of psi is d minus 1/2. Here mass has dimension 1, gy is 4 minus d over 2, and h is 2 minus d. This is just for you, another example for you guys of a good theory, healthy theory to think about. Classical scale invariance requires that all couplings, the scaling dimension of all couplings is 0. Is that clear? Classical scale invariance requires that. So here you could set this guy to 0 if these 4, right? This, you'll have to drop it. You'll have to forcefully tune this to 0, right? And this is also the same story. Good. So for example, we saw that scalar field theory in d equal to 1 plus 1d, all terms, all GNs were actually dimensionless. So that was good. This model does not have that property. Good. All right. Another very, very important example is gauge field theory. Gauge fields. So in gauge fields, non-abelian, abelian or non-abelian doesn't change the story. The action, like the field content is the action was the Lagrangian was f squared, which is basically del a squared, right? So the dimension of this should be d, which means that the dimension of a mu is d minus 2/2. Now you had this derivative, this covariant derivative. Every time you write this down, the dimensionality of the two terms better match. That will tell you what the dimensionality of G is, right? So the dimensionality of G squared is 4 minus D. Now something funny happens. This theory, non-abelian gauge theory, as a classical theory, the Yang-Mills Lagrangian has only one coupling, G squared, right? In 3 plus 1 dimensional space times, we are in this sweet situation where the coupling is dimensionless, so that QCD or any Yang-Mills theory in 3 plus 1 dimension is classically scale invariant. The word that's important is classically. Proving that it's not quantum mechanically gauge invariant is one of the Millennium Prizes in math. The fact that there is This is called dimensional transmutation. There is lambda QCD, blah, blah, blah. But all that you need to know is that this symmetry, this is just a classical analysis and it's not respected in quantum world. Classical symmetry is not necessarily, does not imply that your theory as a quantum theory is going to be classically, is going to be, is going to preserve the symmetry. I mentioned this at the end of the last semester. I made a comment about this. If anyone remembers, what was when we're doing QED, we discussed a manifestation of how quantum. So, all right, what we said was that we're talking about gauge invariance and regulators. We said that a theory, if it's said, you can sensibly talk about the symmetry if there is the regulator respects that symmetry. There exists a regulator that preserves that symmetry. Gauge invariance is a principle that should hold classically and quantum mechanically. We want that to hold. Therefore, we had to use dimensional regularization. I said if you have some symmetries of your theory, right, and you want that to be realized as quantum symmetry, then you should use a regulator. There must exist a regulator that respects that symmetry. Now, we're in this setup where there is a classical symmetry, but there exists no regulator that will respect it. So quantum mechanical is going to get violated. But anyway, that's just a comment from the last semester. Good. So there's a big open question. It's a question of a generation. QCD, which is SU3, SU2, whatever, super angles, whatever super angles theory, that 1 in 3 plus 1 dimensions prove that quantum mechanically is not scale invariant, right? That's one of the biggest open problems. All right, so today, what are we going to talk about? That was a brief summary of what we discussed in the last lecture, perhaps like a little bit convoluted summary, but today we're going to talk about, I'm going to focus on scalings and relate scaling to something that you hear a lot physicists just throughout all the time, called conformal symmetry. And I will just advertise very briefly the modern perspective that we have about quantum field theory, and then we come back and do renormalization perspective for the renormalized perturbation theory. Good. So conformal symmetry and modern view of QFT is like a little detour before we get into renormalized perturbation theory. I'll try to throw in these like high-level detours so that you could reorient yourself. Otherwise, you might get lost. Good? Any questions? All right. So conformal group. Remember what the Poincaré group was? Poincaré group were these transformations. These are just translations. These are Lorentz transformations in d dimension, d space-time dimension, or as SOD minus 1 comma 1, right? We said that, yeah, that's what the Poincaré group is, just a semi-direct product of cross product of this with RD, RD minus 1 comma 1. Now we talked about projective representations, and we said that we often think about covering groups, right? Like in the case of spinors, and that group is spin d minus 1 comma 1, right? So these are familiar, hopefully, from representation theory that we discussed. Now, in a theory that on top of these transformations, there is dilatation as symmetry, right? If you put these next to dilatation, you obtain the conformal symmetry. You obtain something. So here's like I'm being a little bit sloppy. You could embed Poincaré group and this transformation in a larger group called the conformal group. So what are the new transformations? This is a symmetry. And on top of it, there is something called special conformal transformation. It might look ugly, but what it is inversion, shift, inverting back. Right? Every time you find yourself confused about special conformal transformations, they are just, there's a symmetry there's a D2 symmetry. Inversion. So x mu goes to minus x mu over x squared. X squared is x mu, right? So if you invert, shift, translate, and invert back, you're going to get special conformal transformations. So a very important question in physics is, are there scale invariant non-conformal theories? The answer to that is yes, as we'll see. I'll actually comment on this, but are there scale invariant relativistic theories that are non-conformal? That's a really hard question. That's a tricky question. It's related to C theorems. It's related to some of the open problems that we still deal with. Okay. Is it clear? So these are the transformations that we're dealing with. The action of special conformal transformation is a little bit messed up, like to imagine, but good. Okay. So the special conformal transformation could be written in this way. This is another way of writing it. I like to think about it as inversion translation inverting back, because I can never memorize this expression. Okay, so the generator of this transformation, you guys remember what it was? What was it? What's the generator of translations? Sorry? Okay. Yeah, but what is that as an operator? Del mu, right? What's the generator of Lorentz transformations? The vector, the killing vector. It's x mu del mu minus del mu x mu, right? What's the generator of this guy? It's x mu del mu. The generator of this special conformal transformation is x squared eta mu nu minus 2x mu del x nu. Well, this is the infinitesimal transformation you derive it. Okay. All right. So we said that we focus on Poincare symmetry because there were the symmetries of flat metric, right? But if you look at scaling, it's no longer a symmetry or conformal special conformal transformations. They're no longer symmetries of the flat metric. Remember how the metric changes under coordinate transformation, del x prime over del x, blah, 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 right? So under conformal transformation, the metric changes by an overall smooth, non-vanishing real function, right? Think about why that's true. Good. Here is one comment in case this is perhaps I'm just going to mention quickly and forget about it for now. Conformal transformations lead to such a change in the metric, but there are such changes associated to coordinate transformations. A transformation of this type without touching the coordinates is called wild transformation, right? Do not confuse the two. All right, anyway. So the conformal group that I've represented it in D, RD comma 1 is a group that you could actually show as SOD comma 1. 2, sorry. SOD comma 2. Right? So it looks, if you were to look at the Lorentz symmetry in a space-time with 2 time directions, in D plus 2 dimensions, this would be the symmetry. You already know the representation theory of conformal group because I explained to you guys in detail the representation theory of Poincare group. The number that you SO D1 comma D2 is sort of like easy to sort out. There are some technicalities and subtleties, of course, when we talk about spinners, blah, blah, blah. But the basic idea I already presented to you guys in the previous semester. As a physicist, all that we need to know and all that I know is SOD. That's the only group I actually know how to deal with. All right. Good. Okay, so Noether charges. We saw that Noether theorem tells you that associated with these symmetries, there are conserved currents, right? Stress tensor was the thing that we found, we defined canonically, motivated by Poincare transformation. So for example, we defined this translation and the Lorentz charges this way, right? And the stress tensor, there was a definition. Hopefully you recall what it was. You could go and look it up. Lorentz symmetry would require this guy to be symmetric, stress tensor to be symmetric. So it's possible to have a theory that's non-relativistic, where the stress tensor is not symmetric, but you have translation there. Now there is a conformal charge. These are you have to derive these. I'll probably assign it as a homework problem. I've written them in covariant form. I don't know if this notation is familiar, but I encourage you guys. Well, you'll work it out in your homework. Dilatation is this. So you take your stress sensor and contract one of the generators with x lambda, right? And the special conformal transformations, because they are vector worth of transformations, right? Inversion, translation in some direction, inversion back. The corresponding charge is k mu, some others that I've defined here. All right. So now let's see what are the requirements of another conservation laws. So P mu dot has to be 0. That tells you that this equation should be satisfied. If you go back to the definition of stress sensor, theta of alpha mu, that's always satisfied by construction. We said that Lorentz symmetry required this guy to be symmetric, right? So that's m mu nu dot being 0. Now, what about scaling symmetry? D mu dot would require will require that the trace of stress sensor is 0. That is the conservation law. So the stress sensor has to be traceless. Special conformal transformation dot, right? The variation of it is proportional to this expression, which would vanish if you have scaling symmetry and Lorentz symmetry. So now remember what I was saying earlier. I said scaling symmetry doesn't imply conformal symmetry, but scaling symmetry and Lorentz symmetry implies conformal symmetry. There are subtleties here, okay? But this is just seeing that these are connected. Relativity plus scaling is naturally pushing you towards conformal transformations. Yeah.
What is the dot again?
Dot?
It is a P mu dot. What is the dot?
Oh, as in like so these are charges. They're defined on a hypersurface. They're defined on codimension 1 surface. You integrate charges over space, for instance, right? So in every time you do that, let's say you define charges, but they're like Hamiltonian, right? So you have to split space-time into space and time. So dot is just when conservation law means
okay.
d dt of it is 0, right? All right. So now again, I encourage you guys to think deeply about scaling invariant non-conformal theories. There's a lot to learn. All right. Great. Any questions? Now I want to take this as take advantage of this and advertise our modern view of quantum field theory. So what I'm going to say right now is a little bit different, but we're going to quickly come back, right? So I just told you that I took the action of massive free fields or interacting scalar field, and I wrote it as a free massless part. Oops, sorry, free massless part, which was a CFD, right? Plus terms that were explicitly breaking scaling invariance. Now, you could imagine that you replace this free massless theory with any conformal invariant theory. So if we had a formalism to understand conformal invariance theories without Lagrangians, or if we had another formulation of quantum field theory that classified for us what conformal invariant theories are, right? We could take them as the starting point of a perturbation theory. Because they're conformal invariant, there would be scaling of fields. There would be fields that under scaling would transform in the canonical way with some power, right? Some power delta, for example. So you pick one of them and you could deform it. This is called conformal perturbation theory. Our grand picture of quantum field theory nowadays is some UV CFT, any CFT, plus some deformation, but some relevant operator. I'll say that in a second. When you hear a statement, this theory is trivial in the UV, it means that in the UV, it's a free theory deformed. So in this sense, all the theories that we're discussing in normalized perturbation theory in this course are trivial in the UV. Sure. Now, the dimensional analysis tells you that the dimensionality of G is D minus dimensionality of O. If G is positive, these are relevant. We said that they grow in the infrared. If G is 0, they're marginal. They do not grow. They do not decay or grow. They remain the same. And if G is negative, these are irrelevant, so they decay. Unless symmetries intervene, this picture is correct. Good. So the conformal perturbation theory is like this. You take some CFD plus G, some O, which is some local operator of scaling dimension delta. That means this statement, right? The theory has a dilatation operator, right? And these guys transform in this way. There are the eigen operators of they're the eigen operators of the dilatation transformation. The dimensionality of G is D minus delta, just by dimension counting, right? Integral of this over space-time should be dimensionless, which tells you that if this delta is between 0 and D, it's a relevant deformation. If it's D, it's marginal. And if it's larger than D, it's irrelevant deformation. Now, this is called the unitarity bound. It's inconsistent for delta to be less than 0, but I haven't explained that at all. That comes out of understanding conformal field theory. So here's a window to non-perturbative definition of quantum field theory, right? If you come up with some non-Lagrangian way of understanding what CFDs are, you have defined a whole set of non-perturbative quantum, some quantum field theories that are not related to Gaussian things. This is usually the high energy perspective. All right, so this is part 1 of today's lecture. We should pause, we should discuss this. The rest is going to be coming back to Earth and talking about renormalized perturbation theory. Any questions? Okay, so going forward, I couldn't decide whether I should summarize the calculation, the one loop calculation we did in the previous part of the course, part 1 of the course for you first, and then continue, or should I not do it? So I decided not to include it in today's lecture. I'll come back to it tomorrow on the next lecture, but it's essential that you remember that even though there were like ugly integrals and we did dimensional regularization and all of that, but it's essential that you remember some of the basic structure. There was the MS bar, we did dimreg, right? Dimensional regularization. You remember what that was? Dimensional regularization was we shifted the dimensionality space-time to D minus epsilon, 4 minus epsilon. That was point number 1. That came at the cost of introducing an energy scale. We must introduce an energy scale mu, right? Because we wanted to keep the propagator, we wanted the propagator to keep the same form. So the dimreg always comes with a scale. That's very essential. That's related to, that's going to play a key role to what I'm going to say. MS bar, which was minimal subtraction with that extra factor of 1 over 4 pi blah, 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 gamma, right? Is a particular way of removing the infinities that we discussed in the small epsilon expansion. Good? So remember those key ingredients. All right, so renormalized perturbation theory. Again, I'm going to try to start a little bit higher level and then get to the calculation. So our LCFD is free massless fields. We start with a bare Lagrangian, right? So I'm going to write it this way. L0 of M0 lambda 0 phi 0 is this Lagrangian. It's a lambda phi 4. Good. So you probably have heard already about seeing already M0 and lambda 0 running, changing. But, well, sorry, M and lambda, well, let me not comment on that. Anyway, what we're going to do, what we did in the past was what we, in the case of QED, was we wrote this Lagrangian as a renormalized Lagrangian for some renormalized mass, lambda r, and phi of r, plus a whole bunch of things that are counter terms. These include all sorts of infinities. These lead to all sorts of infinities. But this guy is well behaved. But these counter terms, we're also going to view them as like functions of this renormalized things. Renormalized perturbation theory is simply the good old perturbation theory we did, but viewing it as perturbation theory for the renormalized field. So these are new interaction terms. We're going to call them counter terms. They come with their own Feynman diagram contribution and vertices and stuff. Right? That's what renormalized perturbation theory is. So let's get the definition first. I'm going to explain it a little bit, actually, next slide, why we do this. So all the divergences are like basically captured in these counter terms. It's essential. I can't stress this enough. It's essential that the counter terms are local. Perhaps at the level of this course, you won't deal with it, but that's important. So in DIMREG, what we did was we knew that dealing with this Lagrangian, calculating any amplitude, right, leads to all sorts of divergences. And we regulated that by going to 4 minus epsilon dimension, and we introduced a scale mu. Because of that, to even split this into two terms involved introducing scale. Right? That was the MS bar scheme. So when I talk about this, splitting something infinite into this infinite piece and some finite piece is not a canonically well-defined thing. So you scheme dependent. MS bar scheme did that for every particular value of mu, right? So for each case, for each mu, you end up for some particular mu, you end up with this Lagrangian. If you pick a different mu, so mu prime, your couplings and fields will change. This is the running of couplings in renormalized perturbation. Another way of saying all of this is in this splitting, there was mu that played a role in how you split these. The fact that the left-hand side, the bare couplings are independent of the mu is the renormalization principle. Maybe I should pause for a little bit for it to sink. The role of mu is in this splitting. That's the scheme dependence. Good? Any questions? This is the high-level philosophy of what renormalized perturbation theory in QFT is. We're going to get down to examples. Renormalization conditions are the rules and principles that tell you about this split. They fix the couplings and the field, they renormalize couplings and the field in terms of the bare couplings and a scale, right? Those are the renormalization conditions. We're good? Okay. So let's look at this a little bit more systematic. Actually, I want to pause here. Is the principle clear? Going forward, what I'm going to explain in the remainder of this course is I'm going to very briefly, very quickly go over what you would get if you did a 5-4 theory without really explaining much. But I trust you guys, we've done much harder integrals, right? And then next lecture, I'm going to redo QED in this lab. And we're going to discuss maybe other theories as well. I don't know, depending on how the time goes. So higher loops as well. Another thing that I want to comment on is higher loops. Okay, so you take your bare Lagrangian, you split it into renormalized Lagrangian and the counter terms. Now, there are all sorts of divergences here in Feynman diagram. So consider Feynman diagram with superficial degree of divergence, capital D. That means what? That means that the amputated diagram, for example, if this is a diagram, there's a loop in the middle, the amputated diagram includes an integral over k. K is the momentum that runs in the loop. K to the power of capital D minus 1. That's what it means to have superficial degree of divergence D. All right. In this particular case, this is 1 over k squared because of this propagator, and then this propagator is 1 over q minus k squared. We make a very interesting observation here. Something that to this day I still find that a little bit magical. I think there must be a very simple mathematical principle behind it. I've never understood it, but if you take a derivative with respect to q from this expression, it will decrease the degree of divergence by 1. You see that explicitly, right? So if you take d plus 1 derivatives, we get something convergent. Therefore, if you integrate back, the diagram you're dealing with is a polynomial in Q of degree D plus a finite piece in Q. So all the divergences are of the form of a polynomial in Q, could be captured in that way. This is the statement I'm just making. If you want to renormalize the theory, this polynomial is all that you care about. Because the whole point is to identify the divergences, right? So let's do some test example, toy examples. Imagine you have an integral I0q, which is integral from 0 to infinity of dk over k plus k, q. If you take a derivative with respect to q, you get minus 1 over q. You integrate it back, you get minus ln of q plus constant. This is the degree of divergence is 0 in this case. The second example is when you have something like this, where the degree of the divergence is 1. You take a derivative with respect to q, you get these two expressions, but you can easily relate them to previous integral, right? So you get, this ends up being a plus bq plus q ln of q. Now the divergences are in these two terms, a and b. The previous case, the divergences were here, in this constant. I encourage you guys to think a little bit more about these examples. I'm gonna say it right now, if you could teach me the underlying mathematics of this, I would love to understand this. I do not understand it deeply. All right. So let me repeat the main result. If you have a Feynman diagram, right, with superficial degree of divergence capital D, you could always split it into finite piece plus divergences, and the divergent terms come as coefficients of a polynomial of degree D in external momenta Q. Now, Q, when I say external momenta, you could have n different legs. It will be an, whatever it's called, what is it? Like it's a polynomial of a certain degree with Q1 to Qn. Yeah. It's a very difficult word. All right. Any questions? So let's go back and take the bare Lagrangian. This is the bare Lagrangian. Imagine a diagram with superficial degree of divergence D, but we said that in this theory, I went over this quickly last time, in 3 plus 1 dimensions, the degree of divergence is only a function of the external legs, number of external legs. So n of 5. We went through the examples of the QED example. In this case, this means that if you care about dealing with divergences, you only have to consider the 0 point, 2 point, and 4 point functions. 1 point and 3 point functions vanish. Why? Any thoughts? I explained the case in QED. What was the principle in QED? What told you that you couldn't have?
In QED, it was Lorentz.
Correct. So it was a symmetry. There was a symmetry that was keeping the vacuum, that the vacuum was invariant under it. But the operator of interest, in that case, a mu was not invariant, therefore the 1 point function had to vanish. Here, it's phi, so it has to be symmetry. What symmetry can you identify in this Lagrangian? Any thoughts? Okay, it's a Z2 symmetry. What is it? Yeah. So that's the symmetry. That forbids odd point functions.
That forbid all odd point functions, right?
Correct. All right, so the analysis that we did tells you that the 2-point function, you could write it as a finite piece plus a plus bq squared, where a and b are the divergences. 4-point function could be written as a finite piece plus a divergent piece part c. So all the divergent terms are ABC. Now, if I want to view these divergences as interactions in counter term interactions, A is associated with phi squared, B is associated with del phi squared, C is associated with phi 4. Is that too quick? I'm going to draw some diagrams and you're going to see it. But remember this in mind. Keep this in mind. All right. So start with the Lagrangian that we had, this Lagrangian. I think, let me copy paste it back. Where was it? Yeah, here. So this is your starting point. This is the bare Lagrangian. You define a rescalar field, the renormalized field, phi of r, such that now L0 is just rewriting of this, right? L0 is half z del mu phi of r squared minus half m0 squared z phi r squared minus 1 over 4 factorial lambda z squared phi r. Phi 0. Good. Now I'm gonna define z minus 1 as little delta z, delta m, and delta lambda. Why do I want to do that? Because I want to write this term as the good old Lagrangian for the renormalized field and couplings plus these bits. I'm going to call these counter terms. This is BAC. Counter terms. Yeah.
So the renormalized Lagrangian always has the same structure as the bare Lagrangian, just the constants change it.
Precisely.
So what was C?
Sorry?
What was C?
Z is just it's the amount that you have to rescale phi with. It's a renormalization. It's called wave function renormalization. That's what it's called. You have to define renormalized fields. Let's call the difference between the two Z. Good. So all I've done, yeah.
And do we always take this renormalization as like a product, like phi is equal to phi r into something, and not like a sum or something like that?
You're asking whether the wave function normalization is always multiplication? Yes. Yeah.
Are there other approaches to this renormalization?
Very, very good. Okay, awesome. Let me take my words back. In full generality, when you're doing renormalization, you should consider any nonlinear transformation of the field redefinition. So why am I doing this? Field redefinitions are redundancies of description. All these calculations are coming out of path integrals. In the path integral, you're integrating over, it's a functional integral. This is the dummy variable of the functional integration. So it shouldn't matter how I change it. That's why I'm doing field redefinition. These simple examples, just linear field redefinition is enough. A shift sometimes might be helpful or not, usually it's not very good. But there could be non-linear field redefinitions that are playing an important role. Like dualities in quantum field theory are all related to those things. Okay, that was a pretty advanced question. All right, any other questions? If there is time at the end of this semester, I'm gonna come back to renormalization group and do it non-perturbatively, define it high level non-perturbatively, and over there you're gonna see the role of field redefinitions. By the way, there's something super deep and at the same time very annoying about viewing quantum field theory observables as scattering amplitudes. Locality that so far I've been so, like it's been a sacred principle, right? You might ask me, what if you do a non-local field redefinition? So you could do field redefinitions that are local, or you could do non-local field redefinitions. So what's the role of locality? I'll not comment any further. All right. Sorry, that was very cryptic. So renormalized perturbation theory is Feynman diagrams with renormalized couplings lambda of R, right? Plus the interactions due to counter terms, right? So if I view this this field theory, this is still my L0 as some perturbation through Feynman diagrams for delta phi of R. There will be the propagator for phi of R, this guy, right? There will be this term, this term, and this term put together is I p squared del z minus del m. And there is the interaction term, the vertex, and then there is the vertex counter term for the vertex. These are, from the point of view of renormalized perturbation theory, these are all legitimate interactions. You just do the good old perturbation theory, Feynman diagrams with these variables, with these things. Why is this p squared del z minus del m? Think about that. It is a little bit confusing. Or for some people, like. All right. Let's see, how are we doing on time? Okay, a little bit behind. All right, so far all I've done is splitting into two sets of terms, right? Counter terms plus the other terms. Now I need my renormalization condition. I need to define MR lambda of R in terms of I have to define renormalized couplings and renormalized couplings in terms of the Baire couplings. I only define so far renormalized field up to a const, right? All right, that is very easy. You recall how we did this, right? In the case of gauge theory, we said that the 2-point function of the renormalized field in momentum space has to be 1 over p squared minus mr squared, because renormalized mass has to be the pole of the propagator. Renormalized fields will have a pole in their propagator as a complex function in the complex p space, where the pole is at the renormalized point. We talked in depth about this. So this is the there could be there could be terms that are regular at p squared equal m squared, right? Oh, sorry, maybe. Yeah, plus I should write it plus finite terms. Do I want to do that? No, I want to put this on shell. Never mind. Yeah. Depending on how you define this. Anyway. Now the vertex. So sorry. For every coupling, you will have a corresponding renormalization condition. This is the renormalization condition for mass. This is the renormalization condition for the 4-point function, right? It basically says that the amputated vertex 4-point has to be minus I lambda of R when you are at S equal 4m squared T equal U equals 0. Do you know why? Why this condition? Think about that. I think it's a one line. Just every time you find yourself confused, go back to the QED perturbation theory we did. We did all of this, not high level, case by case. We're just doing a bunch of integrals. What is, well, I'll come back to this. If you don't quite know what the origin of this is, I'll say it, I'll remind you actually. You've seen this before. I'll remind you a bit. Sorry, let me see. Am I gonna say this actually, or I'm not gonna say this. Whoops, this is my next lecture. I'll say it next week. All right. Yeah, it's not in this lecture. What was S? Do you remember what S was? Yeah, center of mass energy. Yeah, I'll leave it at that. All right. 4-point function. So let's go through this. At one loop, this renormalized perturbation theory will have these diagrams. It will have a vertex, it will have a counter term vertex, and it will have these one loop diagrams. We calculated these diagrams, we found divergences that we regulated in dim reg by introducing scale mu, right? So here you can think of it in MS bar scheme, dim reg, there is some sort of mu dependent, epsilon dependent piece here, right? And requiring this term to cancel precisely the 1 over epsilon term that we were finding in dim reg is the renormalization condition. You want this to cancel it at scale mu, because this term is mu dependent. So that is the renormalization condition at scale mu. So, for example, this diagram, I'm not going to rewrite it. I'll write this next week. Actually, maybe I'll write it next week. But I'm just going through this quickly. You remember that we did this. This integral was divergent. We regulated it. In dim reg, there was 1 over epsilon bar, right? And ms bar prime, the coefficient of it had something, and then we said, oh, we're just gonna in ms bar prime, ms bar, we just discard in a particular way, and that is like picking a particular cross term here, counter term here, right? Okay, so let's call this schematically V of Q squared. V of Q squared will depend on mu and epsilon. And of course, the Mandelstam variable, the Q squared, right? It will depend on Q squared. So then this is minus I lambda R minus these guys, right? STU channels, so minus I delta lambda. Good. So the renormalization condition becomes this expression, renormalization condition at one loop becomes this expression equal minus I lambda. You solve for this and you learn that delta lambda is minus V4m squared minus V naught. This fixes for you the vertex at arbitrary external momenta. So you have a way of extracting the divergences. Now that this is scheme, now you pick the scheme that tells you how your renormalized couplings change as you change the scale mu. Questions? Oh, as I said, like if I was debating whether I should include the refresh your mind and the QED calculation or not, I first decided to go through this, and next week we come back, we will take that gory, like, detailed calculation and just like step by step go through it and see, you'll see that these are all the steps we did actually. In MS bar, we did all of this. All right, so the 2-point function. That was the 4-point function, that was the vertex. The 2-point function is basically I over p squared minus renormalized mass squared minus this mp squared, right? The 1.1 pi diagram. The renormalization condition that says that m of p squared, when p squared is on shell with the correct renormalized mass, should be 0. And these two derivatives should be 0. The ddp squared should be 0. Do you hopefully remember why? What is this condition coming from? Where is this condition coming from? So I said that the 4-point function, because of its degree of divergence, the divergent piece of it is just one constant called C. For the 2-point function, the degree of divergence, it would have two divergences, a constant A plus B Q squared, right? So these are those two terms. I call it Q, here I'm using P. So I'd said this before, in QFT1, you absolutely had to go through the text so that in advance, so that the lecture makes any sense. QFT2, it's even more essential that you read a little bit in advance. Because there's just no way on earth I can regenerate all of this on the board for you. And that's why we have a text. Pesky and Schroeder, whatever text you want, you can just go through it and read about it. All right, so at one loop, just going through this calculation, this MIP squared, which is the counter term thing, is minus I del, sorry, it's not the counter term. This is the renormalized thing that we're gonna set the renormalization condition, has two pieces. One is the contribution of the counter term to the 2-point function this way, and then this is the other contribution, right? This is the one loop. So this is the counter term contribution, and then this is the loop that's proportional to lambda of R, right? Because, yeah. Good. So this expression, you take it, you set these two renormalization conditions, and you learn that lambda of Z has to be 0 and lambda of M has to be of this form. These are all reinterpretation of the MS bar renormalization scheme we did before. This is like more systematic way of describing it. Actually, the chapter on renormalization group in Shrednicki's book is, I think, even more systematic than Peskin. It's very short. I suggest that you read that section. 31, section 31, I don't know, chapter 31 or whatever. Sorry. All right. Okay, so let me summarize. Today we went over two different topics. First, we started by discussing scaling and conformal symmetry and its relevance to renormalization. Then we talked about renormalized perturbation theory. Actually, if I may, I want to go offline actually. I want to say something here. So maybe this helps. In high energy physics, there are two ways to think about a normalization group. In physics. One is there is a UV theory. This is like that theory with lambda. This is the bare theory, right? Lambda 0, M0, all of that. And then you flow towards an infrared theory, right? There's a scale mu here, right? This is mu equal infinity theory, and this is some mu finite theory. If you have the theory at mu1 and mu2, the couplings here, there are no infinities if you're talking about comparing these two theories. There are no infinities at all. These are all renormalized. The infinities come from comparing one of the theory at this scale to a theory up here. right? So recall what the principle was. This is like schematically all coupling. Geez, oh, sorry, if you don't see that. Let me write it here. So this is the key principle. All the couplings, right? G and mu is equal to the G prime mu prime, right? You get divergences when you pick one of them to be infinite, a UV complete theory. Then the distinction between G prime and G, the transformation between the two might involve infinities. This is the origin of infinities in quantum field theory. When we do path integrals, we integrate over all momenta as if they all exist, right? But we know that this is an idealization, right? So the theory should always have a scale. A theory that has, if you're integrating over all momenta, that means that you have the knowledge of, you know about how nature behaves up to arbitrary high energies. That's never the case. We always have an effective theory. Effective theory is defined in terms of a bunch of couplings here and a scale, and we know how to relate. So renormalization group takes a little bit of a different perspective. So in high energy theory, we often think of it this here, the CFT. And then you deform it by some GO, and this there will be a explosive power mu here. This is G dimensionless, right? I don't know if you see that, sorry. So you add to this CFT some mu to some power GO, and then you run. Another point of view that I'm going to try to advertise at some point in this course is later on effective field theory. Effective field theory says, I can't care less about the UV. It's all made up. We don't know about string theory. We don't know about nature of space-time at the shortest distance, but we can still build planes and buildings. We still have a predictive theory. But Newtonian dynamics and the effective field theories that we have, they're always valid up to certain approximation at some scales. Quantum field theory is to be viewed as an effective field theory, right? So we don't know about arbitrary high energy particles, but we still have standard model particle physics. If the theory here is not renormalizable, that's not the end of the world. It just means that between this theory and deep in the UV, something else happens that you don't know about. All right, so you'll also see another principle. I'm just going to say it very briefly. We'll come back to this. That when if you don't have a UV theory, and you just want to start here, as we always do as physicists, in a Lagrangian, you stick to the principles of quantum field theory set. Positivity of Hamiltonian, symmetries, Poincare invariance, derivative expansion, which is separation of scales, right? So you start with del mu phi squared, plus every single term that is consistent with your symmetries. You have to include it. You absolutely have to include it. That's the effective field theory point of view. And actually, even if you don't include it, as you learn, the moment you start running, they all generate it. Renormalization group will generate all of them. So here we're talking about under our G flow, the couplings were running. In principle, you always have all sorts of higher order couplings that might be zero. When you say 5-4 theory, it means that there's a 5-6, 5-8, 5-10, 5-12, 5-12, 5-12 term, but they're all zero. But the moment you start doing RG flow, you realize that it's impossible. It's fine-tuning. They must always run. So if you start by theory, that was lambda 5-4, the mu, that's silly. You're just being silly. All right. Any questions?
He said that like a 5-4, 5-8, or all those things come up when you start running the constants. What about higher derivative things?
Yes, they do.
They come up?
Yeah. Anything that's consistent with your symmetries will come up. Unless there's a big discussion that there is something, okay, no, never mind. Let me not get into too fancy stuff. So anything goes. This is Landau's perspective on quantum field theory. Any questions?
So, let's say here we started with the 5-4 theory,
Yes.
and then we have our renormalized del Z, del M, everything. So now, and these are function of.
Sorry, you mean 5-4 in the UV, the Baire coupling, the Baire theory is 5-4.
Yeah, I mean in the renormalized we have, yeah.
Yeah.
And then we also have an energy scale associated with it, let's say mu1.
With your normalized one, yes.
Yes. So now, when you are saying that all of the 5, 6, 5, 8, then all of them they'll show up. So if I run this mu, like if I change this energy scale, then they will show up.
Yeah.
I mean, I mean, I'm not able to see like how, like.
We haven't, I haven't explained it yet. No, we're gonna, I'm just telling you in advance where this is going. Yeah, we're gonna discuss that in detail. There are relevant operators. Relevant operators are the ones that grow under RG. Right? So they could be very, very small at high energies, like mass. They are irrelevant operators. Relevant operators are bad. Why? Because you can never really pick them to be small. They grow in the UV. They mess up this theory, right? That's why including irrelevant operators seems like an offensive thing.
So basically the entire logic is that if for relevant operators, it's because they go to 0 at UV, so that's when we start from a conformal theory and then we go down, and that's when they start appearing. So
this is a relevant deformation, yes. You cannot deform by irrelevant deformation because it destroys the fixed point. It destroys the, I mean, you can, but that's not a.
you can fit this thing.
Yeah, there's no split. There's no split. Yeah.
What about marginal?
Marginal. Okay. So marginal. So here's well, let me pause this because I'm going on tangents now.